Okay, everyone, now it's time to try out a few example problems. So what do we have here? Well, a beam segment is subjected to internal bending moments at sections A and B. And it's shown along with the cross-sectional dimensions. And we're going to consider area 1 of the 16-inch long beam segment, which is subjected to internal bending moments of 3,300 pound-foot and 4,700 pound-foot. Okay, so what we want to find? Well, we want to sketch a side view of the beam and plot the distribution of bending stresses that are acting at sections A and B. And we want to know the magnitude of those key bending stresses on the sketch. Also, we want to figure out the resultant force acting in the x direction because we've got a difference in bending moment which will lead to a horizontal shear force to make up for that. And then we have to say, well, is this specified area in equilibrium? And if not, we have to figure out what the horizontal force would be to keep it in equilibrium. So let's jump right into this. We can do this. I believe in you. Wait a sec, what am I doing? No, you go off on your own, you try this out, and then you come back. So 3, 2, 1, you tried it, you came back. I'm hoping you rocked it. We're going to find out. So let's see. So first off, what we have to do is, well, that neutral axis, which is going to tell us where our shear stress, or sorry, our normal stress is 0, is going to be the first thing we need to calculate because that's where the centroid is going to be. So how do we calculate that? Well, we find the area of each of our little sections and where their centroids are, and we use our nice little equation, which is simply that the sum of the individual centroids times their area over the sum of the area is going to be equal to my overall centroid. So I do that. They're all rectangles, which makes it pretty simple. I get the area, and the centroid of a rectangle, measured from the bottom, is always going to be from at its particular center. So I'm going back a little bit, just jumping back here. That means that for this rectangle, its centroid is going to be right there. For these two, they're going to be right here and right here. But all of those distances we're measuring from the bottom. Okay, coming back to it. And we get that the centroid is going to be 7.56 inches from the bottom. Which makes sense. If it was just that central stem, it would have been 6 inches because it would be half of that. And since we have these two flanges at the top, it's a little bit towards the top because of them. It's been pulled upwards. The numbers make sense, and getting a good idea if a number makes sense is a valuable skill to gain. Okay, so we know what the centroid is. Now we need to figure out what the moment of inertia is. Now these are all rectangles, so it's just 1/12 base height cubed for them all. And so that's the first thing we do right here. The second thing we have to figure out is, well, what is the distance? Okay, what is the distance from this piece of centroid to the actual centroid? And so these two are above it, so it's got a negative distance. And then my central stem right here has a positive distance because it's a little bit below it. We take our areas from the previous table to do our parallel axis theorem. And finally, we can calculate the contribution to the moment of inertia for each of these little segments. And we can add them to get our overall moment of inertia, which will be 346.5 inches to the fourth. So this is the equation we used here. This is just their moment of inertia around their centroid using that equation. And then we have to add on this correction term because they're not on the actual centroid. Now, what about that bending stress distribution? We know what the moment of inertia is. We know what our internal bending moments are. So we should be able to calculate everything. And we also know the distance from the neutral axis, which is y. So with all of that, we can set this up. And for this, we're using the whole sigma x is equal to negative my over inertia. Okay. And having done that, well, what do we get? Well, we're going to have a maximum of 506.765 psi on the left in tension and 864.659 in compression. And 721.756 psi and tension on the right, and 1,231.483 psi at the bottom. We can then also, if we want to, create a resultant force for all these different vectors. And we can do that either above or below the centroid, whichever one you want. But we run into an issue here. We run into an issue in the fact that there is a difference. This is not an equilibrium. So we're going to have to figure out a way to solve for this. If you're wondering where we got these forces from, it's simply from the area of these triangles. The area of those triangles. Okay. I know it's really hard to see, but if you zoom in right here, you can see that they didn't include that little tip of the triangle, which is why this is technically the area of a trapezoid, because it didn't actually go down to 0. We're not doing it from the neutral axis, we're doing it from this top section where we have those two flanges, which is slightly above the neutral axis. Now, once we know what the two resultant forces are for the left and the right, we can find the equilibrium of that area. And so we see there would have to be a horizontal shear force of 683 pounds to keep it in equilibrium. And so in this case, this horizontal shear force will be directed from section B towards section A at that interface between area 1 and the stem. So we had that shape earlier, and it's saying that it is going into the page right here. We can tell it has to go that direction simply because this vector has to be pointing that way. This one's smaller. It needs help to balance this out. Okay, I believe that's everything for this one. Let me check. Yep, we're off to a second example. So thank you all for listening, and I will see you all next time. Have a wonderful day. Bye-bye.